All right. Good afternoon, guys. So, any question? All right. All right. So the last day we discussed about an interesting stuff. Um, we looked into that how in a crystal we can have energy gap. So to remind you one more time, if we start to analyze the atom, individual atom, we know already that an atom has some discrete energy levels, right? It cannot have any arbitrary energy levels, and the reason is electron behaves like a wave, so you cannot fit any arbitrary waves in a in a in between two hard walls, right? It has to be some finite number of waves, and that's why there are some finite energies. Now, if you bring many quantum wells close to each other, then because of the interactions between those quantum wells, they create another energy bands. So if I bring two quantum wells to each other, let's say each of the quantum wells have two energy states, I bring both of them together, then because of the interaction between them, each of these energies will be split into two different energies. Okay, so previously we had two energy levels at each of the quantum level, and now we have four different energy levels at all the quantum levels. Okay, so if I bring infinite number of quantum wells, they will actually create infinite number of energies. But the interesting stuff is it will not go over all the places. It will create a bunch. So between each bunch of energies, we will have some certain region where the energies will not be allowed. These are called prohibited energies. No energies will be allowed in that particular band. And we showed that how it looks like in terms of using chronic penny model. So to remind you that we started with a single quantum well. In a single quantum well, we have waves that look like the following. Let's say this is the first wave and this is the second wave. So each of these case, lambda must abide by some certain formula. Let's say this is your L. So lambda must look like the following, where n is 1, 2, 3, all these integer numbers. And that's why energy is also finite and discrete. If I bring many quantum wells close to each other, let's first start with 2. So each of these quantum well, when they were separated, they had two different energy levels. But now, because of the interactions between the waves, you know that the waves are going to spill out, right? They will have a tail. And the higher the energy, the bigger the tail. So both of these guys will start to interact to each other because of the tail, okay? Because of the tail here. And by the interactions, after you have some interactions, you will see that the new system will have, instead of two energy states, they will have four energy states. Okay, they will have four energy states. If I bring another one, another quantum well, now they will have two bunch of energy states. In each bunch, you will have three energy levels. No, it's just equal to n. Okay, the total number of atom would be equal to total number of energy in each bunch. Okay, so each of this bunch will have n number of energy states. Oh yes. So if I have, let's say I have two bunch let's say if I start with a quantum well which has two different energy levels, then of course your total number of energy is going to be n multiplied by 2, twice n, right? Okay. And the other interesting thing is that if you bring infinite number of quantum wells, then these energy levels will be infinite, right? Many levels, energy levels. And the interesting thing is, although there are infinite number of energy levels, you will have some certain space where you will have no energy levels allowed. Okay. So in between these gap, you will have no energy which is allowed. Okay. And this is known by using the chronic penny model. Chronic penny model says that if you have infinite number of quantum wells, then the energy and the wave vector k, ek, has to abide some certain formula. And that formula is written as E cosine alpha A divided by alpha A. Actually, I made a mistake. So from chronic penny model, we know that the EK diagram, it must follow these particular equation. We have not derived that where does this equation come from. It's not within the scope of this current course. But given that this is the relation that we have to abide by, we looked into that what are the different energy levels that might be possible in such a system where we have infinite number of quantum wells. So we did the following. We plotted the left-hand side of this equation, and we wanted to see that whether these left-hand side, it remains within the boundary of plus and minus 1. Why plus and minus 1? Because we know that right-hand side is a function of cosine. So the value of cosine cannot go beyond 1 or cannot go below minus 1. So that means if the left-hand side has to equate with the right-hand side, the left-hand side must also abide by the same maximum and minimum, minus 1 and plus 1 value. And we looked into the plotting in Mathematica. We have noticed that if I take the value of p to be very small, let's say 0.1, and try to plot this function in the left-hand side, we see almost everything. Almost the entire plot is within plus 1 and minus 1 bound. Okay. But if I increase the value of p, remember that what is p? I'll go back here. So p is actually a function of the potential well and the lattice constant, and alpha is a function of energy. Okay. So when I plot this guy, in the x-axis, I'm plotting the value of alpha. Okay. In the y-axis, I'm plotting the value of the left-hand side of the equations. So when I change the value of alpha, that means I'm changing the value of energy, right? So look at that. If I change the value of alpha, that means I'm changing the value of energies. And I notice that if I keep plotting the value of alpha, remember that alpha is just a function of energy. So I'm trying to see that which energy, if I plot back into these equations, is going to remain within -1 and +1. And I notice that if I make a plot like this, I get some curves, and this curve, sometimes it goes beyond the allowed limit of -1, +1. So I know that whenever it crosses beyond -1 or +1, those are the energies which are not allowed. Okay, for instance, in this case, in our case, if I increase the value of P, remember that increase the value of P can be done by increasing the lattice parameter. That means if you take those atoms further away from each other, P would go up. Okay, so for a crystal where the atoms are further away from each other, look at the corresponding energy bands. So look at that. So from 0 to all the way up to this point, all these energies corresponds to a function which is greater than 1. So this means you cannot have any energy which lies in between these values. You will only have some energies from here to there. Okay. Again, you will start to see no energy from this point to that point. But then again, you will have some allowed energy from this point to that point. Okay. So these are shown here again. So we are showing the same function where we say that this part of energy is not allowed. Okay, remember that this is the point where alpha is 0. And one more time, alpha is a function of energy. Okay, so if alpha is 0, that means energy is 0. So you can see that energy 0 is not a possible options. Okay, in fact, you cannot have any allowed energies until your energy goes up beyond a certain value. Okay, you will only start to have an energy after this point. Okay, so this is one energy band. This is another energy band. And in between these two energy bands, you will have forbidden gaps. Okay. So remember when we discussed about the stability of atom, we said that in a plain common sense, it may look like that whenever we have an electron, it must be falling into the nucleus. So what really prevents it from happening is that electron looks like a wave, and that's why electron can have 0 energy. Okay? So this is what we also see from the chronic penny model, that you cannot have an energy which is 0. All right. And also look into another interesting thing. If I zoom in, uh, so if I zoom in here, look at the breadth or the width of each of these energy splitting. So this guy versus this guy, or look at here, this guy has some energy bands. These guy also have an energy bands, right? Which one is wider? Do you notice which one is wider? Is it the one which is closer to the middle, is closer to 0 value, or which is farther away from the 0 value? Farther from the 0 value. So the, the farther you go from the 0 value, the wider the energy bunch becomes. Do you know why it looks like that? Remember, we told that when you bring quantum wells close to each other, they will start to interact, but the amount of interaction, it depends on how long the tails are. Okay. So if you take an energy which is very low, the tails will also be low. Okay. If you take two quantum wells close to each other, then the energy which is at the very bottom, that will have the lowest tail. The energy which is way above, that will have the biggest tail. Okay, so this is why bringing two quantum wells to each other will create energy bunch for sure, but which energy bunch would be splitted further away? It is actually these energies which will be splitted more wider because they have the highest interactions. Okay, do you follow these things? The energies which are higher, they have the highest interactions. Okay, and the higher the interactions, the bigger the energy splitting is. Okay, so this is why if you go high energy, you will see that energy band is becoming bigger. Okay, this is exactly what tonic penny model also shows, that if you have if you take an energy which is close to zero value, give me 1 second. Let's see if I can. So for this guy, which is close to zero value, the bunching size is very small, but this guy would have a bigger bunch. In fact, if you go further and further away, you'll have even bigger bunch. Okay, so all these things, they actually match with our previous understanding. So from here, we know one important stuff, that energy cannot be any arbitrary value. Energy we can create a bunch of energies, but in between each bunch of energies, there must be some levels which are forbidden. And this is the reason why we see energy band gap in a semiconductor material. Okay. So we know about energy, but how about the other part of these equations? Remember that we got this plot by only plotting the left-hand side of the equations. And the left-hand side of the equations must be equated with the right-hand side of the equations. The right-hand side is actually cosine Ka. So it's a cosine function, and it's dependent on the wave vector K. So if I draw both K and energy E, I would get the following. So let's say in the x-axis, I'm plotting K. So the value of K, I'll write it as integer multiple of A divided by pi. And this is minus A by pi. Actually, the other way around, actually. Give me 1 second. So this is 0, and this is pi by A, and then 2 pi by A. In a similar way, on the right-hand side, we should have minus pi by A, minus 2 pi by A, so on and so forth. So these are the values of K. And if you plot the energies, it will look like the following. Yes. Oh, really? I'm so sorry, guys. Let's see if I stop share and can you see it now? Okay, thank you for pointing it out. So we are talking about E and K. So this is E and the x-axis is K. So if you plot E and K, you would notice that E and K looks like the following. Energy and K, it looks like almost a parabola. And then when you reach some certain value of pi by A, you will notice that energy in between this guy and that guy is forbidden. And again, energy would be allowed from this value to another values. Once you reach 2 pi by a, again, energy would take a jump and then look like this. And this value would be symmetric. So eventually, E and K diagram would look like the following. Okay, so look at that. Energy is allowed from here to there, but energy is not allowed in this range. Again, energy would be allowed in this range, but energy would not be allowed in this gap. Okay. So whenever K hits the value of pi by a or 2 pi by a, you will see that energy actually jumps. Okay, energy energy makes a quick uh, jump from one value to another value. Why it is like this? It's because on this plot, when we are plotting the energy versus the left-hand side of the equation, whenever it hits a value of pi by a, it goes beyond these allowed energy levels because it exceeds -1. And it starts to reappear within the allowed value once it goes 2 pi by a. Okay, so this is why the E and K diagram look like the following. Okay, so this EK diagram is actually very important for us because you'll see that by looking into EK diagram, we will know that whether an electron would be able to conduct current or not. Okay. So in case of a free electron means an electron that is not bound by any potential wells. It is not bound by any atoms. Okay. In a free electron, the EK diagram follows a very simple formula. It comes from this. We know that energy is related to p square by twice m. P is the momentum and m is mass. And from Broglie's relation, P is equal to hk whole square divided by twice m. So if you plot the EK diagram, this is energy, this is the K value of a free electron, it would just look like a parabola. Okay, so this is the EK diagram of a free electron. Okay, and a free electron, I mean, as the name suggests, it's very good because it can conduct freely. But the question is that there is no such thing as free electron. It's just a fictitious stuff. In an atom, in an isolated atom, there is electrons, and all these electrons are bound. Okay. So if you take an infinite quantum well, you know that your energy and the K value is always going to be discrete. So in an infinite quantum well, the E and K value will take some discrete values. For instance, you may have the first value here and the second discrete value here, third discrete value here, fourth discrete value here, something like this. Okay, but they will never form a continuous band. And now, in case if you have many quantum wells in a periodic manner, then your EK diagram would look like this. It will look like an almost parabola, but because of the forbidden energies, the moment the value of K hits the value of pi by a, it starts with a jump and eventually it would look like this. Okay. So this is the EK diagram for nearly free electron. In a one-dimensional crystal. Okay. Why crystal? Because a crystal means it's periodic arrangement of atoms. If you have many atoms, all periodically arranged, that forms a crystal. So for those cases of infinite quantum wells, you will have an EK diagram like this, where you will have some energy states which is allowed, some energy states which are not allowed. Okay. And there is an interesting way to plot this EK diagram in a folded manner. So instead of making the entire wings, people plot it in this way. They fold everything. So whenever it starts from here to there, instead of writing it that way, they plot it this way. And instead of again plotting the next band here, they plot it here. Okay. Why they plot it like this? Why they fold everything? It's because if you look at the expression of so if you look here, you will notice that the right hand side of this equation of the that we get from chronic penny model, it is a cosine function, and cosine function is a periodic functions. Okay, so cos ka cosine ka is a periodic function which repeats after every value of 2 and pi. So this is why whenever you hit a value of pi by a, you can actually fold it back to the origin. Okay, so this is why instead of making a plot like this, you can use this periodicity and fold everything back to a single period. Okay, so this is called the reduced EK diagrams. And this is very convenient because you can immediately see that we have some certain energy gaps here. We'll also have some certain energy gaps here. We may have some certain energy gaps here, so on and so forth. Okay, so you will see in our future reference that we particularly talk about these band where EK diagrams looks like this. You will have one convex shape exactly like this and one concave shape like that. Okay, so this is called the conduction band and this is called the valence band. Okay, these conductions and valence bands are very important in order to determine whether the device, the material is going to conduct current or not. Okay. The other thing that might be important for us to know, how much time do we have left? 10 minutes, okay. So we can cover, I think. So the other important thing about EK diagram is that this diagram is symmetric around the zero value. Okay, so this means if you have a positive K value with a given energy, you must have another state where you have the same energy but negative K. Okay, so look at this guy. So look at this guy. It has It has EK diagram, look like this. And because of its symmetric shape, if you have a K value with a given energy here, you must have the same energy, but an opposite K value, which is here. Okay. So same thing is also here. If you have a positive K value with a given energy, you must also have a negative K value with a given energy. Okay. Now, why that matters? Remember that K is related to the momentum. Momentum is what? Mass multiplied by the velocity, right? So positive K actually means positive velocity and negative K means negative velocity. Okay. So this actually means when we talk about the positive K, we might be referring an electron going from left to right. If we talk about negative K, we're actually talking about electron going from right to left. Okay. So in a material, if you have electrons going positive from left to right and also electron going from right to left, what would be the total current? If you have same number of electrons going from left to right and right to left, should be zero, right? The current should not have any net values. Okay. So in order to create current, we need to create an imbalance between how much electron is going from left to right versus how much current is going to the other directions. Okay. So this diagram actually tells you that what happens when you create this kind of imbalance. So if you take a material and if you apply no bias voltage, then you will see the electrons are going to capture all these states in a symmetric manner. Like if an electron have a negative K value with a given energy, you will also see another electron will also take a positive K value at the same energies. Okay. So this is why in a material, electrons are actually flowing. If you take a silicon materials, no matter whether you apply a bias voltage or not, electrons will always keep flowing. Okay. But the thing is that the number of electrons going left to right and the number of electrons going right to left are equal. And that's why there is no net current. So once we apply some bias, we create the imbalance between the flow. So by applying some bias, we create these situations. Look at that. It shows that what happens when we apply a bias voltage. So a bias voltage actually creates the imbalance. So you will see that depending on whether the bias voltage is positive or negative, some electrons will have some higher energy with some higher K value, let's say negative K value, which are not compensated by an equal amount of positive K value. Okay, so you can see some dots here, and you can see that some dots are colored with blue and some dots are not colored. Okay, basically they are saying that the dots which are not colored are unoccupied. These are energy states, these are allowed energy states, but there is no electrons which exist on that states. Okay, so because these kind of imbalanced distributions of electrons, there will be net current. Okay, so it looks like we have more negative K value. Okay, now depending on what is your actual axis reference, it will definitely have some particular direction of current. No, there will be some certain net current. Okay, so we know that how to explain the conductions of current in a material when we apply some bias. One more time, if you apply no bias, you will see there are electrons, but the electrons are symmetrically going to occupy negative K states and positive K states. Once we apply some bias, you will create an imbalance between negative and positive K states, and that's why it will conduct some net current. And also, there is one more interesting thing here, which I'll show in the whiteboard. So let us see what is that thing. Let us say we know about EK diagram that we just learned, and we know that E and K would take some values, but the most interesting part is here where the EK diagram looks like this. Okay, one convex and one concave part of the EK diagrams. And the convex part is called conduction band. Oh, I'm so sorry, man. Thank you so much. Thank you. I'm so sorry, guys. I don't know why it just keeps shutting off. So we are talking about EK diagrams, and we are writing the convex and concave part of energies. So one part is conduction band, one part is valence band. Now, let's say these are the allowed energy states, right? So you start to put electrons on these systems one by one. Let's say you put the first 2 electrons, you'll go here, okay, at the very bottom energy levels. You put the second set of pair of electron, it will go to the next higher energy levels. You'll put the third pair of electrons, it will go here, fourth probably here, fifth probably here, sixth probably here, so on and so forth, okay? So now there is a famous um, postulate made by Pauli. It's called Pauli's principle, and it says that an electron can occupy only a certain energy states. So no two electron can share the same energy states. Okay, it's like a seat in a classroom. Like if the seat is already taken by one particular guy, the next guy must be looking for some another seat. Okay, so in a similar way, give me just 1 more minute and we'll wrap up. So we're saying that if we have EK diagrams, each of these points on this EK diagram basically means some sitting arrangement, some chairs on a classrooms. If an electron already comes here and occupies that, then the next electron must find a different places to sit. Okay, so if you fill up this entire band, entire valence band with electrons, and let's say now you decide that you will apply a bias voltage. I said that in order to create when you create a bias voltage, it creates an asymmetry between positive K states and negative K states, right? So in this situation, if you apply a bias voltage, let's say I apply a positive bias voltage. So I'm hoping that some electrons will have more positive K states than negative K states. But if you really want to make this electron moves, let's say I want to these electron to move from here to there. Okay. But in order to really make this electron move, you need to find a seat which is already empty. And if all these seats are already taken away by other electrons, no matter how much bias you apply, you will never be able to make a conduction current. Okay. It's because the seats are all filled up. So in order to really make a conduction happen, you have to somehow excite some electron so that they leave, let's say they leave this guy, and some electron must leave this space and they should go here. Okay, so previously the electron was here, and now in some way, we will talk later that how it can be made possible, but in some way, if you can make this electron go to the other energy levels and make this seat empty, then you can actually push some other electron from here to there. Okay, and then you will might be able to create some imbalance between positive and negative K states. So this is the case when you will have some conduction currents. Okay, we will go into more details here, but for now, let me tell you this, that this is the reason why in a PN junction silicons. If you apply bias, you don't see the current to flow immediately. You have to apply some certain bias. Let's say whenever you have a, that you have a diode have a cutoff frequency or cutoff voltage, let's say 0.7 volt cutoff voltage. It's actually because before you apply 0.7 volt voltage, there is no empty seats where an electron can go from negative K state to positive K states. It's only after you apply that cutoff voltage, if you apply a voltage beyond 0.7 volt, you can make some electron go from valence band to the conduction band, so that the seat becomes empty, and now you can create some imbalance between positive K states and negative K states. Okay, so in later course we will know more about it, but this is one big interesting thing that only comes out from quantum mechanics. Like if you try to apply the classical mechanics and try to explain that why silicon, it does not conduct current beyond a certain threshold voltage, there is no way we can explain this. Okay, so we'll see in the next class that how it might be made possible. But I took some extra time, sorry for that, guys, but thank you so much for your patience. Hopefully we'll meet next week. And you know that the